Today we will be going to present our project, which is enhancing HLS4ML. Before getting started, I would like to introduce to my team members. I am Anshu and my teammates are Aba and Zhonghua. Now, what is the main motivation behind this project? We use PyTorch and TensorFlow frameworks to design machine learning models and deploy it on general processors, CPU and GPU. This makes our life simple. On the other hand, if you want to deploy such networks to a specific hardware such as ASICs and FPGAs, you need to write the hardware code from scratch and the entire development process takes months. But why do people still want to use it? Because FPGAs and ASICs are much more efficient than general processors. Now what's the solution to this? HLS4ML is a Python library which works on solving this issue. It takes neural network models and directly synthesizes it on FPGA without the need of writing hardware code from scratch. Now the downside is that it creates a new hardware for each of the layers. This is not scalable for larger models. Hence, we wanted to only create a single hardware to reuse all the layers, and this is what we are aiming in this project. This work will be helpful for physicists at CERN who originally created this library.
As a solution, we developed a system-on-chip design implemented on an FPGA and as an ASIC. Our engine is developed as an axis stream design to which input pixels and weights are supplied through 3 DMAs, controlled by the ARM processor on the PS side of the Zinc FPGA. Our RTL backend, when added to HLS4ML, will produce the tickle file to generate this entire project, system verilog header file for synthesis parameters, and C++ or Python runtime controllers. So here's our workflow. So given a deep neural network, we group the layers into a linear list of what we call bundles. A bundle is an abstraction for the set of layers that can be deterministically run on our system. Each bundle generates the controller code, tiled weights and biases, and the configuration headers. So here's the block diagram generated from the TCL scripts in Xilinx Vivado. We implemented a smaller version of our design with 96 processing elements on a pink Z2 FPGA. We also synthesized the same design on a 65 nanometer GPCMOS PDK to produce these results. You can see the ASIC implementation is about 10 times more performant than the FPGA. Here's the randomized verification of our design. Signals are toggled randomly with a given probability to test all the corner cases. On the left, you can see the output from the design matching exactly with the expected output. We also set up a CI/CD pipeline for our GitHub repository. Whenever the master branch gets updated, the test bench runs with random inputs on GitHub servers to ensure the design is always flawless.
This may seem nice and easy, but in fact, going through the code design and code debug on all 4 levels, which are device, hardware, firmware, and software, is complicated and not exactly always reasonable. For some, we are able to solve them by ourselves or by consulting the people working at CERN. For others, we were able to find a better way and circumvent the problem. And in extreme cases, we decided to give up a development workflow altogether in favor of another one. This is a review of what we have done. We started by exploring the existing backend and parameterizing the RTL engine, and then step by step, test with several neural network layers, and implement our design on hardware devices, while taking care of the firmware. Finally, we demonstrated the functional correctness by running a small network and a large enough one, in our case ResNet 50, which cannot be hosted without our reusable engine. Going forward, we plan to move our design to C++ runtime on Cortex and Darrow. This will free our implementation from constraints of certain types of FPGAs, so it can be implemented and tested with these on any SoC that has an ARM architecture. We also will push the ASIC tape-out by September. Please drop by our project webpage for the source code and wiki. Thank you for being with us all the way. To reiterate, implementing a machine learning hardware accelerator can be difficult, and the HLS4ML is the process through automated pipeline. And we develop our own backend and controller to enhance the HLS4ML with the support for larger networks.